Today we're going to wrap up surrogate-based optimization by discussing infill. It should be a bit shorter than some of our other surrogate-based discussions. We've kind of got through the more difficult pieces. There are, I would say, two broad categories of approaching infill. And if you remember, infill is a process. We had this little block diagram where we started with sampling. And from the sample, we create a surrogate. Now that we have this model, we can perform optimization on the surrogate, right? Because the original function was either too expensive or too noisy to optimize directly on, so we optimize on the surrogate. And we're going to check for convergence. And if not, we're going to, do what's called infill, meaning we're going to create, or we're going to sample another point or points perhaps, rebuild the surrogate, and repeat this process again until we're done for some sort of convergence criteria. There are many variations, but two sort of broad categories are to do exploitation, meaning we're going to try to get to the minimum quickly. And that's going to be using a prediction. It's prediction based on where the optimization tells us the best points are. And then the other is more exploration based. And we're going to use, sometimes it's called error based. But the idea there is that we're not necessarily going to try and converge as quickly. This would be more appropriate if we have a, say, multimodal problem. We want to search the space better. Okay, so let's talk about the first, and this is fairly straightforward. Let me just kind of write it as an algorithm. We could think of it this way, that from sampling first, we'll start with sampling. I'm going to get a bunch of points. So here's my sampling function. And it has some arguments, number of dimensions, and how many samples you want. But anyway, at the end of sampling, we have a bunch of points. And so then I'm going to create my surrogate. Let's just call it create surrogate. And these are the two steps we talked about last time, right? I'm going to feed it all these data points, or better yet, and inside, where I'm going to take some of those data points and partition them off to test data versus training data, so I can do my cross-validation and figure out a model. But once I've established the model, then I don't have to continue that process. I will just create the surrogate here. So this is going to be the surrogate. And after I have the surrogate, so again, these are the two steps we talked about last time. All I'm going to do now is to optimize the surrogate. I'm going to minimize, actually we've been calling this f hat. I'm going to minimize f hat of x. So now I have this alternative function I can use that's quick and cheap to evaluate. So this is a very fast process generally to minimize, and I have a new point. And so now I'm going to add this to my sampling plan. I'm going to say, I'm going to take my original points here, and I'm going to add x star to them. All right, so we'll call this, I don't know, I'll just give it the same name for now. And then the same with f, right? I'm just adding, concatenating to this array, if you will, this new point that I have. And that's really it. And then I just go back to here and I continue doing this loop. So I recreate my surrogate, I optimize the surrogate, and then I take the prediction that the surrogate says this is the best place to go. I'm going to use that as my, I don't have any data there yet, so I'm going to evaluate the function. I do now think the optimization. I'm going to now include that data point or evaluate it. I guess I should put that there. I didn't really explicitly say that. So this is actually not quite right. I guess x star is right. This is x star, and this is f hat star. So what I would put in here is f of x star, like the actual function. So I have to do an evaluation. I'm not going to just take f hat because this is my surrogate. It's an approximation of the true function. So I'm either going to go back and do another experiment, or I'm going to go run my expensive simulation again, add a new point, and then continue forward. That's really it. So I add some criteria. Maybe it's just a number of iterations, maybe better criteria, depending on how smooth things are, that my function isn't changing very much. That's really the process. So here's a simple 1D example. So let's say this is my surrogate model. I have sampled at 3 points. So these are known points, right? This is the true function. And this blue curve is just my estimate. I don't know what the true function looks like, but that's my surrogate. And so I'm going to now optimize the surrogate. And that's going to give me a point here, right? That's the optimum. And now I take that point and run it through my expensive function and see what I get. And notice I got something that wasn't on the curve, which is to be expected, right? My surrogate isn't a perfect predictor. But I took the surrogate and now I I added that point and I rebuilt the surrogate. So you can see this blue curve is different. Before it passed through this point and now it doesn't, because it's a quadratic. So now I've got more points. So it's a regression now. So I'm going to do the same thing. And you can see in this case, I mean, this is 1D, really simple. It's going to converge very quickly. I'm going to sample again somewhere over here and I get a new point. I've rebuilt the surrogate and, you know, about done at this point, right? I didn't really change at all. So this is a very efficient approach. It's the approach that is used in the homework assignment. It'll help you get some practice with it. But it does depend on a good choice of the surrogate. It's appropriate for it. So this will often work well, but there are cases where we can get misled. So here's an example, the same function. Remember, these are just, this is what I'm evaluating at, but let's say the true function actually looked like this. This is the red. This is what it actually looked like. And so I really missed the minimum here. I thought this was a minimum. It was really maybe a local or even a kind of a flat spot, a weak minimum here. And I didn't find it, and that's because I was using a model that was too simple. I was underfitting. I had a quadratic model when the real model, you know, was maybe more like this quartic. It had more variation to it. And so that wasn't a failing of the method per se, but a failing of my choice of the surrogate model. So that's also why we have to do, you know, extensive cross-validation tests to make sure this is a good model. And then we can kind of go through this optimization process. You can see how this can quickly lead me to an optimal solution. That's going to do it much better than I could just by sampling, right? I can sample, but sampling, you know, is going to spread things out. The optimization is going to say, oh, okay, based on where these samples are and kind of this data fit, I really think you should go here. And then we go there. And because now I have new info, I'm going to update the model. And pretty quickly, I'm going to be able to converge to a minimum. It may not be the global minimum if it's multimodal, but especially if it's a unimodal function, this is very effective. Okay, so that's really it for that. The other approach is this exploration-based approach, and it's going to look like this exact same algorithm. We're going to sample, we're going to create a surrogate. But instead of just minimizing the function directly, we're going to use some sort of other metric to choose where to go. And once we choose where to go, we evaluate the function, add this to our data set, repeat the process. So very much the same, but instead of just minimizing, we're going to do something else with the surrogate to help us choose a point so that we're not, you know, maybe converging too quickly. We want to explore a bit. Similar to, you know, maybe kind of the difference between some of the gradient-based and gradient-free approaches. Now, this won't work with all surrogates, the approach we're going to take here. It's based on the methods we discussed at the end of last time that allow us to get an uncertainty prediction as well as a data fit. And so the common ones are called these Gaussian process regression models. Kriging, as we mentioned, is a popular one. But what they look like, again, just to recap, is that I've got some data points, these black dots, and I guess you can ignore the actual function because that's not something we actually know, but just to show you for reference, that normally all we get from our surrogate is this fit, this sort of dark blue line. But with these Gaussian process regression models, I also get sort of these confidence intervals, if you will, or uncertainty intervals. And in this case, these are Gaussian, so these are normally distributed. So it gives me some indication of where things are where I'm more confident in the prediction of the model. So I'm pretty confident about the behavior here because I've got points here and here nearby. I'm really uncertain about what's happening here because I don't have, the curvature is changing. There's a lot of possibilities through here, but this is my best prediction given the limited data so far. Okay, so the way we're going to do this, well, I guess you might pause and ask yourself, how would you choose where to sample next? We said we didn't want to just minimize, so how would you choose where to sample? Okay, so one option, we've got means, we've got variances and all sorts of things. We could say, well, why don't I just sample where the mean of the function is low? So I've got this data fit, and I want to sample where the mean is low. And I guess in that case, that would be right here. That's good, but the problem with that is that it's exactly the same to, it's exactly the same as the approach. I'm just thinking about something, sorry. It's going to be the same as the approach we just did, right? Or more or less, because exploitation was like, let's just get to the minimum. And I should say, I didn't really make this very clear. When we created the surrogate model, we did exploitation. It doesn't have to be a gradient-based method that we use. We often do because the surrogate is usually, most surrogates are going to be smooth and differentiable. And so gradient-based is going to be really efficient, really suitable for that. But it doesn't have to be. We could use a gradient free, or we could use a globalization strategy. That'll help us be more likely to find a global minimum, potentially, right? It may mean that we're bouncing around a bit. So it's not so clear necessarily that it's these two approaches I'm talking about are local versus global. Despite what I said earlier, I'm just kind of rethinking that. I'm realizing that we can actually do both in either case, right? We can potentially still do multimodal functions where we exploit. It's just that we're going to try to get there faster. We're going to optimize the multimodal space, get that best point, and that's going to tend to converge towards usually wherever we find a best point early on. Not necessarily, but since we're getting more sampling there, it's likely that we'll probably still converge towards that. So it still can work, but it seems it's going to be more likely that we'll converge to a local minimum. Okay, so in this case, as we said, mean, not really any different, right? It's the same. We're just going to converge to the best point and then update it. We could say, well, maybe we should sample where our uncertainty is high because we don't know much there at all, right? Like here, I don't know much. So that seems like a good candidate to sample. But on closer thought, that's not necessarily the best, right? Because I don't really care about where the model's uncertain. What I care about is finding the best point, right? I'm trying to do an optimization. I'm not trying to create the best surrogate possible that just agrees, that makes good predictions everywhere. That's not my purpose. Although that is something that surrogates are used for. But in the context of optimization, I'm not trying to create this global surrogate that works everywhere. I'm trying to find the best point that I can for the true function. So just because there's a lot of variance doesn't necessarily mean that's desirable, right? There could be tons of variance, tons of uncertainty, but all the points there are bad, right? Even in the best optimistic scenario, they're still really bad. So we need some sort of better metric. And I should say that if we do just sample the highest variance, that's really not that different from just having a bigger sampling plan. I mean, it's a little better, but it's almost, we're just kind of trying to fill the space and making sure that there's nowhere that we just don't know something about this function. We're trying to get really good coverage. Okay, so the approach we're going to use is called expected improvement. It's an expected value, meaning an average, but it's the average expectation of how much we could improve. So we're going to maximize that. We're going to maximize our expected improvement. There's more details in the book, and I should say that I'm in the process of, have been over the past week, completely rewriting the chapter. So there's a lot more detail in the things that we've discussed. Many of them I've already discussed in these videos. But if you go back next week, you should see a lot more detail if you're interested. Okay, but I'm not going to go through the math. I want to go through the concept here to show you a few plots. Okay, so here's an example. Here's this multimodal function, and here is some points that I already know, and this indicates the best point that I have so far. Okay, and there's some uncertainty here, here, elsewhere, right? There's some uncertainty. So what I'm going to do is that at every single point, I'm going to evaluate what's called the expected improvement. And this is what this looks like. So here's just picking one x equals 0.5. And just keep in mind, I'm going to repeat this at every single x. But at x, if I was to draw my uncertainty, imagine this was sticking up out of the screen. It's not in the same plane, right? So it's basically showing you this light blue section, right? This was an uncertainty bound. So this is that same figure, but just kind of projected out. So in other words, this mean here corresponds to the mean. And this is like a, I don't know, 2 sigma, I think, standard deviation perhaps. And so we're just kind of showing that probability distribution in a little more detail. So there's some probability that the function is way over here, but based on our best estimate, that's very, very unlikely. We expect it to be somewhere within this range. If I was to evaluate the function, I think it's here. So what's expected improvement? Well, this is the best point I've found so far. So we've drawn this line here to indicate a reference value. And let me see if I can make this a little bigger. Let's say I drew this. Let's zoom in a little bit. Here's that probability function. That's where I think the point, or that's my probability of where I think the point is. And here's that reference point, okay? And just here's another reference line. So my expected improvement is the integral, or the area under the curve below that line, right? Because everything above this line is worse. Anything that did end up above this line would be worse than my best. And if I found anything underneath here, it would be better. It would give me an improvement. So the probability that I'm going to get an improvement is the integral of this curve from here to here. So I'm going to calculate that at every single point along my curve, or along my surrogate in general, and calculate what's the probability that I'm going to get a good point here. Notice this is different than just that there's high uncertainty. It's not just there's high uncertainty, but there's enough uncertainty in the region where I could expect an improvement. So again, this example maybe doesn't illustrate it quite as well, but imagine this part of the function here had big uncertainty bounds here, right? If we were to draw the Gaussian for this part, it would come up and there'd be a big uncertainty here. And even though there's tons of uncertainty, that's not really interesting to us, because the probability that offers improvement, in other words, the integral from below this line, is very, very small, right? There's a possibility the function all of a sudden takes a nosedive, right? But based on the data that we have and the type of, our best estimate of the model, the type of surrogate we're using, in this case, a Kriging, then, we don't expect there to be, or we expect only negligible possibility of that improvement. All right, so if I was to compute this, as we said, at every single x point, repeat that process again and again, this is what it would look like, right? So you can see there's a bump here. We expect that there's a high probability improvement here. There's also a bump here. We expect there's improvement here. And notice that it's not as high. So in this case, we're pretty confident about it, right? Because the uncertainty is low, but there's just not that much room that we think below, right? There's not that much room to go down. So the expected improvement is actually lower. So anyway, the process here is that, we evaluate expected improvement everywhere and we pick the maximum. So in that case, that would be here. So what we do is this would become our new sample point, right? Wherever this is here. And we'd evaluate the function, and, I don't know what the true function is. Maybe it's here. Maybe it doesn't actually offer us as much improvement. We rebuild the surrogate, redo expected improvement, and just iterate, right? In the same kind of process, we're going to do that usually right until our function value isn't changing, or until some budget of iterations. If this is expensive, we may not want to, we may want to have some cap on the budget, right? Because we're running experiments or expensive simulations. Okay, so that's really it. It's a fairly basic process after we've developed the surrogate and done a good job with sampling and creating a surrogate. From then on out, the optimization part we're very familiar with by now. And all that happens after that is choosing where to evaluate. And it's either going to be usually one or two approaches, where we take the minimum of the function, or we do a probabilistic approach like expected improvement and then choose that point. And sometimes some of these methods will not just choose one point. Like I mentioned with the exploitation, say you had a multimodal function, right? Here I just showed a single modal. We could do the same problem where we just take the minimum I guess this one as I outlined here, but it could be multiple points, right? Like if it was multimodal and we expected that, maybe we take a few best points, put them in. The reason why we usually only do one or a few, right, is because remember, this is expensive. So we carefully budget it in our sampling. That's the part we can control. We know for sure how many it's going to take because we chose that. We don't know how long this is going to take to optimize. And so we want to be really careful, right? Like every time we get new data, that costs us a lot. That's assumption, right? It's expensive. And so because it's expensive, we want to use that data right away. Recreating the surrogate is inexpensive. Re-optimizing, that's inexpensive. The bottleneck is going out and running that experiment again or running that high fidelity simulation again. So often it's one because we just want to kind of use that information right away. The rest of that is just really quick, comparatively speaking. But sometimes, there'll be strategies where we'll use more than one point. And so, yeah, there's some variations there. Anyway, that's it for surrogate-based optimization. We're going to talk about optimization under uncertainty next week.